So we are going to continue our program with the next paper from the Institute for Manufacturing Technology and Production Systems from the Technical University Kaiserslautern, who is co-chairing this conference. So the authors are Christopher Gläßner, Nicole Krenkel, and Jan Aurich. The paper is entitled Energy Simulation of Diffuse Deposition Modeling Process Using Machine Learning Approach. We are looking forward to your presentation.
Dear professors and colleagues, hello. My name is Li Yi and come from China. Currently, I'm a PhD student at the University of Kaiserslautern, and today I'm going to talk about my paper, Energy Simulation of the First Deposition Modeling Process using Machine Learning Approach. In this presentation, I will first talk about my research motivation and background, and afterward I will talk about my research framework, including the data, training approach, and the results. And finally, I will summarize the presentation with a brief conclusion and outlook. Machine learning summarizes computation of statistical models and algorithms to perform specific tasks. And today, machine learning has shown a high degree of maturity. Many different approaches like random forest algorithms, artificial neural networks have been widely implemented for example, image processing, sound recognition, and data mining. So under this background, we were thinking about whether we can also use these machine learning approaches to realize energy simulation of manufacturing processes. Because current simulation approaches for manufacturing processes are based on physical modeling, which suggests us to look into the insides of the system and then describe them using physical variables like current, voltage, heat flow, and so on. And usually, physical modeling-based methods are very complex, and the development of simulation is very time-spending. So if we can use machine learning to realize the energy simulation, then we can save more time and effort. Under current research background, additive manufacturing was once considered to have more sustainable advantages against conventional manufacturing processes. But current research also states that the energy efficiency of the process may be not good. So the investigation and the assessment on the energy performance of different additive manufacturing technologies and processes are emerging research tasks. So in this study, we focused on the first deposition modeling process, and we try to implement the machine learning to enable the simulation, energy simulation. And the picture left side shows the general system structure of FDM. As can be seen that there are usually two material rolls, and the operating head can move in XY plane to melt the material and squeeze them on a platform. And currently, there are many different machine learning approaches like artificial neural network or random forest algorithms. And in this work, we only focused on the random forest algorithms, which belongs to a typical assembly learning approach based on decision trees. Decision tree is a tree-like model of decisions and possible consequences, and has been widely used to support decision makings. For example, if we have a data set of survival probability of Titanic, we can use the decision tree to map the relationship between the genders, ages, and ticket class and the final survival probability. And this type of machine learning belongs to supervised learning, so we need two basic information, two types of information, the features and the labels. In this case, in this example, the genders, ages are regarded as the features, and the survival probability is regarded as the label. And the trained model can be used for future prediction. For example, if I can make a travel with a ship or a train, then I can use this decision tree to see my decision. For example, I'm a male, I'm an adult, so if I take the sheep, I got 20% survival probability if something bad happens, so a wiser decision may be just take the train. The random forest is based on the aggregation of many trees. Well, if you got one decision tree, that's a tree. But if you have many decision trees, you have a forest. And if we assume that each tree will get a part of the entire data set and does training, then we're talking about a random forest. For example, if you have 100 data items and each decision tree will take 19 of them and do trainings, so each decision tree will be unique. In the future, if you give new data for validation V, then every decision tree will make its own prediction. And the final decision of the random forest is equal to the decision of the majority of decision trees. For example, if you got 10 decision trees and 2 of them says yes and 8 of them says no, then the final decision will be no. And if we apply machine learning, we usually got a problem of overfitting. For example, if you have a data set with 4 data points, then you have different strategies to approach those data. For example, you can just use sign function, and as can be seen that the curve, well, the function and the 4 data points are very well matched. And also, if you got another strategy, for example, linear regression, we can be seen that the general behavior of the 4 data points are described, but it doesn't fit well because between data points and the line there's still gaps. And in the future, if you got a new data set looking like this, then the linear regression is still functional, and the other one, the sign function, is no longer feasible because, like I said, if the curve fits the original data too well, then it may lose its general capability for other data sets. And for machine learning, we need to avoid overfitting. And in order to reduce the risk of overfitting, we combined 5 basic random forest models, and then we proposed these so-called hybrid models. All these 5 models are already developed by other researchers, and if you want to know more information about them, please see the references in my paper. And the motivation for combining those models is that, for example, if one model has overfitting, we still got another 4 models. So using this hybrid model assembling, we can reduce the risk. And the research object is a Ultimaker 3, which is a typical 3D printer and belongs to the process FDM with, for example, printing head, transmission systems. And the research consists of 3 phases. And in the first phase, data acquisition, we printed this small part, the wear support, and then we use a power meter to capture the power data. And afterward, we got a data set called DS. 70% of the data set is used for fitting the models, do the training, and the remaining 30% is used for validation. After the second phase, we got a hybrid random forest simulator, the trained model, which can be implemented for further energy simulation. And of course, for the energy simulation, we did another experiment and used the same process condition to do the simulation, and then finally we compared their results. Like I said, this research belongs to typical supervised learning. So we got 2 types of information. The first one is feature, and in this research we use the G code as the as the raw dataset because G-code contains all necessary process information. And for the labels, we applied power meter to capture the power values. And as you can see that this is a screenshot of our data sheet, and we got time, voltage, current information, but in this case we just need the power value. And the raw material sets cannot be directly used for training, so we need to process them and combine them together. This picture shows the screenshot of our new data set for training, and as you can see that in this new data set we have only numbers, and because in the G code there's still some text like G, X and Y, but for machine learning only numbers can be recognized, so the text in the raw data sets are converted into numbers. And afterward we use the data set as the training to do the training, and after the training we use 3 statistical indicators to evaluate the training quality. And during the training, the loss function will be evaluated and minimized. In this case, as you can see that for the first 4 models, there's no significant differences between MSE, MAE, and R-squared value. XGB, the last model, shows significant differences. And usually, if MSE and MAE are very low, then it means that the model is matching the data set. And the R-squared value varies only from 0 to 1. If the R-squared value is very high, it means that the capability of the prediction of the trained model is very high. But like I said, in this research, 70% of the data set is used for training and 30% is used for validation. If the capability of the prediction is very high, the risk of overfitting is already there. But like I said, using a hybrid model, we can significantly reduce the risk of overfitting. And in this case, if XGB is overfitted, we still got another 4 models without overfitting. And in the third phase, we applied the trained model into an energy simulation, and as you can see that in the early stage of the model, the prediction is not well, the prediction is a little bit higher, but during the middle stage and later stage, the prediction is very well. And to my opinion, the reason for why the simulation accuracy is so high may be that we used one same part for both experiments, because the geometry of the product remains the same, so the most X, Y, Z position information are exactly the same for both experiments. So that's the reason why the simulation is so good. If we try to use the trained model for other parts, the result may be different. But in this case, in this study, we only focused on this part. So according to the result of the simulation implementation, we may say that the machine learning approach is feasible for developing energy simulations. Now, summary. With respect to our study, the first conclusion can be made that random forest algorithm is a powerful tool to develop energy simulations of FDM as well as additive manufacturing. And second, using hybrid model is able to reduce the risk of overfitting. For the future works, like I said, we use the one same part for both experiments. So in the future, we need to validate the trained model with other parts and to see whether it is still feasible for other cases. And second, in this research, we only focused on the random forest algorithms, and in the future we can compare our results with other machine learning approaches like artificial neural network. That's the end of my talk, and thank you for your attention.
Thank you for sending us this video. We have just watched and listened to the presentation of our co-chair for the conference, Institute for Manufacturing Technology and Production Systems from the Technical University in Kaiserslautern. The presenting author is Li Yi and is going to be answer some questions in a minute. So the paper was entitled Energy Simulation of Diffuse Deposition Modeling Process Using Machine Learning Approach. Li, can you hear me?
Yes, I can hear you.
Great, thank you. It was very interesting to listen to your contribution. Could you maybe give us a bit more detail about the challenges for future work?
Yeah, thank you. In current state, we have applied the model for one experiment, and like I said, in the validation experiment, we use the same product. So in both input data, there are many similarity. So in next step, the challenge is whether we can use the trained model for other products, which means that is our trained model general feasible for other application scenarios. This will be our biggest challenge.
Okay, thank you. And did you have a chance to apply your approach in an industrial environment so far?
Yes, that's a very big issue because the background of this research is that we want to propose a very easy and convenient method to quantify the energy consumption in the design phase. So the motivation is that in current research state, the energy consumptions of different additive manufacturing processes are very high. And also this results in more, for example, energy cost. And as we discussed in previous paper, the cost has been a big issue. So if we can reduce our energy consumption, so first we can reduce our energy cost. Second, we can improve our sustainability profile of additive manufacturing. So the next step is that if we can confirm that our model is feasible for all products, then we can integrate the developed approach to energy performance optimization, assessment, and cost reduction in industry.
Thank you for your answer. It was very interesting to listen to our comments. How or through which parameters do you look at the sustainability profile?
Well, currently we are now focusing on this inventory analysis level. So in the future, if we want to calculate the impact indicators, our first choice will be cumulative energy demand, which summarizes the primary energy expenses of the product life cycle.
Thank you very much for your answer and also for your time for answering these questions.
Thank you very much.
See you soon. Bye.
See you. Bye.
So